All right, this is going over the second part to counting particles in substances. We're going to start on number 10, which is where we left off last time. A gas occupies 12.3 liters. Liters measures volume, so that's our volume. At a pressure of 20 millimeters of mercury. So that's a pressure. What is the volume when the pressure, so we're looking for our volume, when the pressure is increased to 60 millimeters of mercury. So a new pressure is 60. So that means the first volume and pressure were our initials. The second pressures are second. And then now we're looking for a new volume, so we're looking for our V2. We're still going to use the combined gas formula, but we're only going to focus on volume and pressure. We don't need temperature at all, so we're just going to cancel that part out. So our equation's P1 V1 equals P2 V2. So P1 V1 equals P2 V2. Plugging in our numbers, P1 is 20, V1 is 12.3, and that's going to equal P2 is 60, and V2 is what we're looking for. So when solving this, we're going to multiply 20 times 12.3. That's going to be 252. And that's going to be equal to 60 V2. And so then we're going to divide both sides by 60. So 252 divided by 60, that's 4.2. So that means V2 equals 4.2. Since our first volume was liters, that means our second volume is also liters. Number 11, a 0.6 liter sample of gas. So that is our volume. Sample of gas is warmed from 77 degrees Celsius to 86 degrees Celsius. These are both temperatures, but they're both in Celsius. So we're going to have to convert them to Kelvin by adding 273. So my first temperature is 77 degrees Celsius plus 273. And then my second temperature is 86 degrees Celsius plus 273. 77 plus 273 is 350. 86 plus 273 is 359. And then we're looking for our new volume. So that means 0.60 was our first volume. We're looking for our V2. Since we're dealing with volume and temperature only, we're still going to use our combined gas formula, but we're going to cover out the pressure. We don't need P, so it's V1 over T1 equals V2 over T2. Now I can plug in my numbers. My V1 is 0.6. My T1 was 350. My V2 is what I'm looking for. And my T2 is 359. When we're solving the problems and they're set up like fractions, we're going to cross multiply, do the butterfly method. So we're going to multiply across. We're going to do 0.6 times 359. And then we're going to divide by the number that's left over. We're going to divide by 350. That's about 0.615, so we're going to round that to 0.62. So V2 equals 0.62. Since our first volume was in liters, our second volume will also be in liters. All right, number 12. Determine the pressure change when a constant volume of gas at 1 atmosphere. So we have our pressure. is heated from 20 degrees Celsius to 30 degrees Celsius. So we have two different temperatures and they're both in Celsius, so we have to convert them to Kelvin. So T1 is 20 degrees Celsius plus 273. T2 is 30 degrees Celsius, so plus 273. And then we're looking for our new pressure. So that means 1 atmosphere was our first pressure. All right, changing our temperature, 20 plus 273, that's 293 Kelvin. 30 plus 273, that's 303 Kelvin. We're only dealing with pressure and temperature, so looking back at our combined gas law, we don't need volume, so we're going to cancel that out. So it'll be P1 over T1 equals P2 over T2. First pressure is 1. First temperature is 293. Second pressure is what we're looking for. Second temperature is 303. Remember, we're going to multiply across. We have 1 times 303, but 1 times any number is the same number. So then we're really just going to divide 303 by 293. 303 divided by 293. That gives us about 1.034129. So I'm going to round that to 1.03. So that means my P2 equals 1.03. My first pressure was in atmosphere, so I'm going to do my second pressure in ATM. All right, let's go to number 13. Isotopes are 2 or more atoms of the same element that have the same number of something but a different number of something else. So they're going to have the same number of protons, which protons is equal to atomic number on the periodic table. Don't forget that. And they're going to have a different number of neutrons. And since the neutrons are different, the mass is also going to be different, because mass is protons plus neutrons. Number 14, rubidium has 2 common isotopes, rubidium-85 and rubidium-87. If the abundance of rubidium-85 is 72.2% and the abundance of rubidium-87 is 27.8%, what is the average atomic mass of rubidium? And the formula for finding that average atomic mass, again, it's going to be the mass times the percentage plus the mass times percent. And since we only have 2 isotopes, that's really it. Then we're going to divide by 100. So our first mass, rubidium-85, has a percent of 72.2. So we're going to do 85 times 72.2 plus, then our next mass is 87, and that percentage is 27.8. 87 times 27.8, and then we're going to divide that by 100. It's really important that we do the top row first, then hit enter in our calculator, and then divide by 100. Otherwise, the order of operations will mess this up. So we're going to do parentheses 85 times 72.2 plus 87 times 27.8. So that's 8555.6 divided by 100. The mass is about 85.556, so we're going to round that to 85.56. And that is our mass of rubidium. It's important to point out that your mass, your final answer, should be between the two numbers that are given to you as your mass. If we were to get anything outside of the range of 85 and 87, like maybe a 72 or a 94, then we know we did it wrong. The average should always be between our numbers given to us. All right, let's go to 15. Calculate the average atomic mass of oxygen if its abundance in nature is 99.76% oxygen 16. So that's our percent and that's our mass. So we're going to do 16 times 99.76 plus 0.04% oxygen 17. So that's 17 times 0.04% and 0.20% oxygen 18. So we're going to add 18 times 0.20%. It's important to keep in mind also that the percentages play a role in our final answer. Since we have a greater percentage for oxygen 16, our final answer should be really close to 16. Whichever number has the highest percentage, that's what our number for our final answer should be close to. So we're going to multiply all the tops and add them together, and then remember to divide by 100. In our calculator, we are going to do 16 times 99.76 plus 17 times 0.04 plus 18 times 0.20. And then we're going to divide this number by 100. That's about 16.0044. Which would just be 16, which again is very close to our highest percentage oxygen. I'm just going to leave all those numbers there. Number 16, determine the percent composition of all the elements in CaNO3 2. So to do this, we're going to need to find the individual mass of every element, and then we're going to divide that by the total mass of the whole compound, and then multiply it by 100. Remember, at the end, all of our percentages should equal up to 100%. So first, let's count the atoms. We have 1 calcium. We have a 2 outside of a parentheses for N and O, so that means we're going to have 2 nitrogens. And since we already have 3 oxygens, we're going to do 2 times 3. That makes 6 oxygens. So calcium is just 1. And if we look at our periodic table, we can see that calcium is 40.078. Nitrogen is 2. So we're going to do 2 times the mass of nitrogen, which is 14.007. And then oxygen, again, 3 times 2 is 6. So that's 6 times the mass of oxygen is 15.999. We know 40.078 stays the same, but we're going to do 2 times 14.007. That's about 28.014. And then 6 times 15.999 is 95.994. And then we're going to add all of this up to get our total mass. 40.078 plus 28.014 plus 95.994. Our total mass is 164.086. Now we can do our percentages. For calcium, we're going to do the mass of calcium divided by the total times 100. So calcium will be 40.078 divided by 164.08. times 100. 40.078 divided by 164.08 times 100. That's about 24.43%. Next, we're going to do nitrogen. That's 28.014. Divided by 164.08 times 100. 0.014 divided by 164.08 times 100, 17.07. And finally, we're going to do oxygen, which is 95.994. Divided by 164.08 times 100. That's about 58.50, so 58.5%. Remember, if we did it all correctly, all three numbers should equal up to 100%. So 24.43 plus 17.07 plus 58.5. And yes, that's 100%, so we did it correctly. Let's go to number 17. What is the empirical formula for C4H6? When we're working this out, remember, we're going to divide by the least common denominator. So with my numbers 4 and 6, we'll start with the lowest number, 4. Can both be divided by 4 evenly? No. Can both be divided by 3? No. Can both be divided by 2? Yes. So C4 divided by 2 and H6 divided by 2, that's going to give us C2H3. That is our empirical formula. That is our simplified answer. Number 18, a compound is found to contain 86.5% of Na, 25.4% of S, and 38.1% of O. Find its empirical formula. So this problem has about 3 steps to it. The first thing we're going to do is convert all of these percentages into mass, and then we're going to divide each mass by its molar mass on the periodic table. So let's go with the first one, Na. We're going to do 36.5 grams instead of percentages. And then we're going to divide that by the molar mass of Na, which is 22.990. And then let's set up the other ones before we calculate them. Then we're going to do 25.4 S, so that's grams. Then we're going to divide that by the molar mass of sulfur, which is 32.066. And that's 1 mole. And then we have our oxygen, which will be 38.1 grams. Then the molar mass of oxygen is 15.999. And then 1 mole on the top. All right, so now we can plug it in. 36.5 divided by 22.99. That's going to be 1.587, so we'll round that to 1.59. Then we're going to do sulfur, 25.4 divided by 32.066. That's going to be about 0.7921, so I'll keep that 0.79. And then we're going to do 38.1 divided by 15.999. That's going to be about 2.38. Next, we're going to divide all of these numbers by the smallest number. The smallest number is 0.79. So we'll divide all of these by the smallest number. So 1.59 divided by 0.79, that's about 2. For S, any number divided by itself is 1. And the last one, oxygen, 2.38 divided by 0.79, that's about a 3. So that means our formula will be Na2S1, we don't write ones in chemistry, and then O3. So that'll be Na2SO3. Finally, number 19, find the molecular formula for a compound with a mass of 78 grams and the empirical formula CH. So the first thing we need to do is find the mass of CH. So carbon is 0.11 and H is 1.008. Add that together. That's about 13.019. Then we're going to take the mass that was given to us, 78 grams, and we're going to divide that by the mass we figured out from our empirical formula. So 78 grams divided by 13.019. So we're going to do 78 divided by 13.019. That's about 5.99. Which rounds to 6. So that means we're going to multiply each subscript, which there's none. So if there's none, really it's C1H1 times 6 times 6. So that means the molecular formula should have been C6H6. All right, and that is all for the counting particles in substances review.